Swayam Prabha. Digital India. Educated India.
Welcome to the next lecture. In this module, the same preparation of alkyl halide we will be continuing. We will be studying now the preparation of alkyl halides from alkanes and alkenes. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayam Prabha, MHRD, New Delhi. The topics that we will be covering in this particular session include preparation of alkyl halides from alkanes, basically X2 in the presence of light or heat, then HX addition to symmetrical alkenes, HX addition to unsymmetrical alkenes, Markovnikov and anti-Markovnikov rules, then finally X2 addition to alkene. Let us look at the synthesis of alkyl halides from alkanes. We have so far seen the synthesis of alkyl halides from alcohols. Next we are moving to another starting material, which is the alkane. So from alkanes, that is from the hydrocarbons, we can actually make alkyl halides. So the reagent used in this particular reaction is halogen. So alkanes and halogens react to give alkyl halides. So the conditions required for this particular transformation is light, heat or catalyst. So any one of the thing is required for this particular transformation. So the alkane, which is RH, reacts with X2 in the presence of H nu, that is light, or heat gives RX, that is alkyl halide, plus HX. This is formed in this particular reaction. We have two reactions represented here. We are starting from a simple alkane, which is propane. Reaction with chlorine, that is the chlorination, gives two products. We are getting a primary alkyl halide and a secondary alkyl halide, but the ratio of the product formed are 45% and 55%. Roughly 1:1 ratio we are getting the product. This is the chlorination reaction. But on the other hand, if the propane is reacted with the bromine, that is the bromination reaction is carried out, we are actually getting the primary alkyl bromide as only very small amount, which is 3%, whereas the secondary alkyl bromide is formed in major quantity, that is 97%. The same way, if we take a isobutane also undergoes chlorination to give 65-35 ratio of the primary and the tertiary alkyl halides, that is chloro derivative, whereas when we take the bromination, we get only a trace amount of the primary alkyl bromide. In other words, we can say this is not at all formed. It's formed in very minute quantities, but the tertiary bromide is formed in large excess or 99+%. Now we will have to see why or how this particular difference happens when we run the chlorination reaction or bromination reaction. So let us look at the mechanism of alkane halogenation. So in this particular case, the reaction of halogen is homolytically cleaved to give two halogen radicals. So this reaction is the initial stage or the initiation reaction. So the alkane halogenation reaction is a free radical reaction. The XX bond is a very weak bond, so it can easily be homolytically cleaved to produce the halogen radical. So X2 gets cleaved to give 2X dot. This is the initiation step. And the X dot reacts with the alkane to produce HX and R dot. So this is one of the step. And in the next step, this R dot reacts with the X2, that is the halogen, to produce Rx and X dot. So this is a propagation reaction. And in the last step, the termination, this alkyl radical, in the termination step, these two react together. The alkyl radical and the halogen radical both combine together to give Rx. So that is the termination step. So the other termination step includes the R dot and X dot can combine together, that we already know. Other than that, this R dot and another R dot can combine together in the termination step. R dot, two molecules of R dot can combine, or two molecules of X dot can also combine. So these are all the other additional termination steps. So Rx can combine together to give the product, or two R dot alone can combine together to give a product, or two X dot can combine together to give a product. So these are all the different termination steps that are involved. In the first step, we have initiation, where X dot is formed, followed by, in the propagation step, alkyl radical is produced in the first step, which reacts with X2 to produce the Rx, and in the termination step, alkyl radical and the X dot both combine to give the Rx. So this is the mechanism for alkane halogenation. So let us look at the mechanism for this particular transformation. So this is the starting material which we saw earlier, which is the propane. The X dot reacts with this alkane. There are two protons can be abstracted. The first one is the primary hydrogen can be abstracted. That is abstraction of primary hydrogen. The second one, this CH2 proton can also be abstracted, which is the secondary hydrogen. So there are two possibilities of the X dot radical abstracting a proton from this carbon or from this carbon. So if it abstracts the primary hydrogen, then we end up with a N-propyl radical, and this N-propyl radical reacts with X2 to give the N-propyl halide. On the other hand, if the abstraction is on the secondary hydrogen, we end up with the isopropyl radical, where the radical is carbon is in the central carbon. This reacts with X2 to produce CH3 CHX CH3, that is isopropyl halide. So if we take X dot here as a chlorine, then we will end up with a chloride here, and here also we will end up with a chloride. And if we look at the stability of the radicals, that is primary, which is less stable compared to secondary, which is less stable compared to tertiary. In other words, tertiary alkyl radicals are more stable compared to primary alkyl radical. So based on that, we can actually predict how the reaction will proceed. And when we talk about the reactivity and the selectivity, we earlier saw chlorination gave roughly 1:1 ratio of the products. This is because we have a early transition state as shown here, due to which the chlorination actually gives the 1:1 ratio, whereas in the case of bromination, we have a late transition state. So when we say late transition state, that means this is very close to the product. So that is what is called the late transition state. When we say early transition state, the transition state resembles very similar to the starting material. So that is the reason here both are giving 1:1 ratio, whereas in this one we have a stable radical. So between the starting material and the radical, which one reacts very quickly is the one which decides the product distribution. So between these two, we already know this isopropyl radical is more stable compared to the N-propyl radical. So that is the reason in the bromination reaction, this is more stable radical. So this gives the isopropyl radical or the observed product. If it is a chlorination reaction, then what happens is this is what is very close to the transition state. So that means we have equal probability of formation of these two radicals. So reaction mechanism can be explained based on the transition state of this particular radical reaction. Let us look at HX addition to symmetrical alkenes. Let us look at how the HX adds to the alkene. Here the HX addition to alkene is a electrophilic addition. Let us find out how do we decide whether it is an electrophilic addition or not. Now, the HX can be polarized towards the most electronegative halogen, because as we know, halogens are more electronegative elements. So the bond HX is always polarized towards the halogens. So there is a more electron density around the halogen atoms. So because of this, the HX bond cleaves in a heterolytic way. When it cleaves heterolytic way, we have two species. One is a electron rich species, that is the X minus. Another one is a electropositive or electrophilic species H plus. Now between these two individual species, which will add across the double bond. Now the X minus is electron rich, alkene is also electron rich, so they both repel each other, so they don't add in the first step. Since we know the X minus cannot add to the alkene double bond, what can happen is the H plus, which is electrophilic in nature, which is electron seeking, can be attacked by the alkene. So the alkene electrons are transferred or given to the electron deficient H plus. So the bond forms between the one of the carbon and the hydrogen. Now we have a symmetrical alkene here. So it doesn't matter whether the carbon number 1 or the carbon number 2 adds to the hydrogen or the proton. We end up with the intermediate carbocation. So in the first step, what we end up is formation of a carbocation. So once the carbocation is formed, then what can happen is the X minus, which is electron rich, can now attack the carbocation to form the final product. So in this case, hydrogen adds to one carbon and the X adds to another carbon. So this is the second step. So the overall reaction, that is the HX addition, is electrophilic in nature. The electrophile H plus adds to the alkene first, followed by the X minus addition. So we have a final compound as shown here. So what we can say is when H plus adds, the resulting carbocation should be more stable. So this is what is the reaction, how it happens. But in this particular case, we have a symmetrical alkene. So whenever we have a symmetrical alkene, it doesn't matter whichever way the proton adds, it will still give the same carbocation. But in other cases, we will be looking at soon about the unsymmetrical alkenes addition. Okay. So in a symmetrical alkene, the HX addition is still electrophilic in nature. Let us now look at HX addition to unsymmetrical alkenes. Alkyl halides can be prepared from alkenes. So the reagent used is basically HX, and the conditions used are either with hydrogen peroxide or without hydrogen peroxide. The hydrogen halide adds across the double bond to give the hydrogen alkyl halide. Generally, the reagent HX is used as a gas, that is a dry hydrogen halide is used as a gas in a protic solvent, preferably in acetic acid. We need to avoid aqueous solvents for this reaction because use of water produces basically an alcohol. The important reaction, the rule which governs the HX addition to alkene is a Markovnikov rule. So according to this rule, when there is a unsymmetrical alkenes, that is we have a methyl group here, there is a hydrogen here, we have a hydrogen and hydrogen in the second carbon. So when we have two or unsymmetrical alkene, the HX can add across this double bond in two different ways. One is the hydrogen adds to this carbon, or the hydrogen can add to this carbon. So that results in regioisomers. Two isomers are possible when we have unsymmetrical alkenes. But in this particular reaction, we are not getting isomers. We are getting one product as the major product. So Markovnikov identified this first, and then he proposed the Markovnikov rule. According to this rule, whenever there is a HX that is added across an unsymmetrical alkene, the negative part, which is the iodide, adds to the most substituted carbon, that is the most branched carbon the iodide ion adds, and the hydrogen adds to the other carbon. So this is what is the Markovnikov product. So if we take another alkene where we have two methyl groups here, and there is one methyl group and a proton in the second carbon, when HI add to this one, the I minus basically adds to the most substituted carbon, and hydrogen adds to the other carbon. So this is what is the Markovnikov rule. We are already familiar with the HX addition to a symmetrical alkene. So the reaction is basically an electrophilic reaction. The first step is the addition of proton to the double bond, which results in a carbocation formation. So this carbocation is attacked by the X minus halide to give the final product. So this reaction we already know, and this is a symmetrical alkene. In the case of unsymmetrical alkene also, the reaction proceeds in the same fashion. The first step is the addition of H plus, followed by the second step, the addition of X minus. In the presence of hydrogen peroxide, the intermediate formed is bromine radical and not the bromide ion. The steps involved are given below. In the presence of hydrogen peroxide, The intermediate is bromine radical, we know that. So how the bromine radical is formed, we will see here. In the first step, the hydrogen peroxide gets homolytically gets cleaved to form two hydroxyl radical. This hydroxyl radical reacts with HBr to give the water and bromine radical. The bromine radical now adds across the double bond to give a carbon radical. The stability of this carbon radical decides where the bromine will add, whether it will add to the first carbon or the second carbon. Decide is based on the stability of the resulting carbon radical. In other words, the most stable carbon radical is formed. The simple HX addition to alkene is a electrophilic reaction. So let us compare Markovnikov and anti-Markovnikov reactions. The first one is electrophilic addition, whereas the anti-Markovnikov is radical addition. In the Markovnikov reaction, the H plus is the first one which is added to the double bond, whereas in the anti-Markovnikov addition, it is the bromine radical that is added to the double bond. In the case of Markovnikov reaction, we don't have a peroxide, whereas in the anti-Markovnikov reaction, we have peroxide. And all hydrogen halides give Markovnikov reaction, whereas mainly HBr only gives the anti-Markovnikov reaction. So this is how we can compare between Markovnikov and anti-Markovnikov reaction. So let us recap. Markovnikov reaction, the first step is electrophilic addition, whereas in the anti-Markovnikov it's the radical addition. So the first step is addition of H plus, whereas in the anti-Markovnikov it is the addition of bromine dot. The next one is addition of X2 to alkenes. Let us look at the addition of X2 to alkene. So here we have an alkene and X2 is added to this alkene. Because X2 is a symmetrical molecule, when we add the X across the double bond, the obtained product is also, whether it is symmetrical or unsymmetrical, does not make any difference. So we add the halogens across the double bond. So between the halogens, iodine is too slow to react and fluorine is too fast, that means explosive reaction. So basically iodine and fluorine are not used in this particular addition reaction. In other words, iodides and fluorides are not prepared using this particular method. This leaves chlorine and bromine to be the best suitable reagent for the preparation of alkyl chlorides and alkyl bromides. Let us look at how the addition proceeds. So the bromine adds across the double bond. This is polarized and this actually is having a delta positive charge because this is electron rich species. So bromine negative charge cannot add to this double bond, rather a delta plus charge only can add to this double bond. So the intermediate that is formed is a cyclic bromonium ion intermediate, and this leaves the bromide ion separately. In the second step, the bromide ion comes and attacks any one of the carbon. Either this carbon can be attacked or this carbon can be attacked. So the bromide ion attacks any one of the carbon, releasing the bromine to the other side. So this is basically a anti-addition. That means the groups which are added are in the anti-orientation. So this is what is called anti-addition of bromine across the double bond. In the summary, we had seen the preparation of alkyl halides from alkane that involves use of X2 in the presence of light or heat. That reactions involve radical mechanism. We also studied about HX addition to symmetrical alkene. Either it is symmetrical alkene or unsymmetrical alkene, both undergo the reaction using electrophilic mechanism. There we studied about Markovnikov and anti-Markovnikov addition, that is use of hydrogen peroxide or without the use of hydrogen peroxide. In the presence of hydrogen peroxide, the reaction mechanism is radical mechanism, and in the absence of hydrogen peroxide, it is very similar to the electrophilic addition mechanism. And finally, we also studied about the X2 addition to alkene, which is again electrophilic in nature. With this, we conclude this session on preparation of alkyl halides from alkanes or alkenes.